This is Math 139, and we're looking in Section 1.8 at solving inequalities that are quadratic. We're going to start our discussion by looking at the inequality x squared is greater than or equal to greater than or equal to 8x minus 12. In order to do this, I'd like to examine this analytically, graphically, numerically, all of the different ways that we've discussed. I'm going to begin graphically, picking up on some of the techniques that we used in our last section. In our last section, we said that if we graphed both sides of an equation, the graph could help us out. It could tell us some things. That's also true when I graph both sides of an inequality. So I'm going to graph the function x squared and also the function 8x minus 12, and let's see what the graph might tell us. In this case, I'm going to use the online graphing tool, Desmos, and in order to be able to do that and still draw on the graph as we talk about it, I've actually printed out my results, but you can just do it on the computer. Here's what I got. The graph that's in blue is my x squared graph, and the graph that is in orange is the 8x minus 12, the linear piece or the line. When we were solving equations, we had noticed that the intersection points actually gave us the solution to the equations. In this case, we can see here there's an intersection point at 2, 4. And there's another point up here at 6, 36. If I were actually on the computer, I could, of course, just click on the graphs, and Desmos would tell me those intersection points right away. All right. Well, I don't really just want where they're equal this time. I would like to know where is x squared greater than or equal to 8x minus 12. And in order to answer that question using the graph, I'm going to say, well, where is the x squared graph, the parabola, larger than the linear graph, the orange one? As we look across our graph, it looks like the parabola is above the line at first, and it continues to be above the line for quite a while. All the way, in fact, until I get to that intersection point. So everything I've highlighted satisfies that inequality. X squared is bigger than 8x minus 12. Now everything changes at the point 2, 4. For a while in here, you can see that the line is actually above the parabola. The y values for 8x minus 12 are bigger than the y values for x squared. And that's not what we want to have happen based on our inequality. So I'm going to skip over this for a while. And then notice it changes again at the intersection point 636. At this point, once again, the parabola, x squared, becomes bigger than, or above, the line 8x minus 12. These graphs are hints to the solution that we're looking for. What we really want to have happen again is for x squared to be greater than or equal to 8x minus 12. And it looks like that's true for all of the x values until I get to x equal 2. So x less than or equal to 2 makes this true. All of these points corresponding to x values less than or equal to 2. But it happens again over here. All of these x values that are greater than 6, actually greater than or equal to 6, will also work. And again, I'm using the greater than or equal to and the less than or equal to because of the original had the equals in it. In interval notation, this would say our solution goes from negative infinity to 2, and then also from 6 to infinity. So on the graph, we can see how to solve that inequality. Let's take a look at the table of values as well. Notice we want the x squareds, all of these values, to be greater than or equal to the 8x minus 12, all of these values. That is certainly true at first. The blue is bigger than the orange. And it continues to be true here and here. Right there, they're equal. That's that intersection point 2,4. And so all the way until I get here, from negative infinity to 2, the x squared numbers are bigger than the linear numbers. Now everything reverses. X squared is smaller. The blue is smaller than the orange number. Here, here, and here. Until we get to 6, where they're once again equal. And then we pick up again with the blue, the x squared being larger than the linear number. So you can see using the table of values as well that our solution goes from negative infinity to 2, then skips for a while, and picks up at 6, and keeps on going. A table of values like this is helpful to illustrate numerically what's going on, but in more complicated problems it would be less useful because sometimes the intersection points aren't nice whole numbers. So I picked a special example so I could use the chart here. All right, how would we do the same problem using just the equation, analytically? Well, the first thing we seem to need to know is the intersection points. We need to know that 2 and that 6, or we'll never get to this answer. So analytically, I'm going to start by saying, let's go ahead and solve what I'm going to call the related equation. To get the related equation, I just take my original inequality and replace the inequality sign with an equals. We know how to solve quadratic equations. Usually we start by getting them to equal 0, so I'm going to do that. X squared minus 8x plus 12 equals 0. And this one I believe I can factor. X squared would be x times x, a sum of negative 8, and a product of 12. I'm thinking negative 2 and negative 6 would do that. And so x minus 2 equals 0, or x minus 6 equals 0. And there are those intersection values, x equals 2 and x equals 6, that we saw when we looked at the graph. All right, how am I going to get from that to these two intervals? Well, essentially, if you remember the graph, everything changes at the intersection points. If the parabola is above the line, it continues to be above the line until we get to that intersection point. Then the line's above the parabola for a while, and it doesn't change again until we get to the intersection point. So if I'm working by hand without a graph or a table of values that the calculator or computer has generated for me, one thing that I could do is I could just test specific numbers. I'd need to test some number over here smaller than 2. I'd need to test some number in between the 2 and the 6, and some number above the 6 to see whether in that interval my inequality is true or false. So let's do that. I'm going to test my inequality. The way I'm going to do that is to draw a number line, and I'm just going to put x equals 2 and x equals 6, the two solutions to the related equation, right there on my number line. I know that if I choose just one value in each interval, whatever happens for that one value will be true throughout the entire interval. So for example, what if we were to test x equals 0? Is our inequality true at x equals 0? Well, let's see. If I were to plug in 0, I would get 0 is greater than or equal to negative 12. And that certainly is true. Let's try another one. I only need to pick one point within the interval because things only change at the intersection points. So let's pick 3 this time. And once again, I'm going to check to see whether my inequality is true. So I'm going to plug in the 3. Is 3 squared greater than or equal to 3 minus 12? That is 9 I'm sorry, what did I do? Let me try that one more time. I forgot the 8. I have an 8 times 3. There we go. Is 9 greater than or equal to 24 minus 12? Well, that's not true. 9 is not greater than or equal to 12. So that's false. And then one more time. Let's pick a number bigger. Let's just say 10. Pick anything you want as long as it's bigger than 6. If I start with my inequality again, plug in the 10. Is 100 greater than or equal to 80 minus 12? Well, yeah, 100 is greater than or equal to 68. So that's true. After having done the test, I can see that my inequality was true down here, from -2 down to -infinity. And it was also true from 6 up this way, from +6 to +infinity. There, then, are my final answers. Sometimes we use this little union sign to join them together. One comment I'll make before we move on to the next video is that although I was very specific and wrote out my test by hand on all of these, it would also be fine for you to use a table of values generated by your calculator to do the test. So for example, if I choose the test point 0, it would be fine for me to go over here to my calculator and say, oh, is 1 greater than or equal to, 0, is 0 greater than or equal to -12? Yes, that's true. And then I went to the test point 3. At 3, is 9 greater than or equal to 12? No, that's false, and so on. So I wrote out my tests by hand, but it is okay to use the table of values on the calculator or computer to do the calculations for your test as well.